The pH going to be very close to for number 1 after it's done?
Neutral, perhaps.
Which is what number
7.
on the scale?
7.
7. So where's the pH going to be approximately? And you don't have to give a number. You could just say a region of the pH scale. Where's the pH going to be for number 2? Because what are we using to titrate?
Strong base.
Okay. And what about scenario 3? Where's the pH going to be?
Less than 7.
Okay. So let's look first at our strong acid, strong base titration. You've got 3 times 10 milliliters of 0.50 molar HCl. I hate it when the College Board and stuff does this. Guys, this is just 300, right? Or 30, I'm sorry, 30. Why didn't they just say 30, right? But sometimes they like to do that. So you do need to be ready. So guys, pro tip, brush up on your scientific notation. You know, that's where you have something times 10 to a power. Technically, what power would this one be to?
10 to the 1.
10 to the first, right? All right, so we've got 0.5 molarity HCl titrated with 0.5 molarity NaOH. So we're going to find the initial pH of just the 0.5 molarity HCl. Guys, A is easy. Am I right when I say it's easy?
No.
What do they want? They want the initial pH of HCl.
Yeah.
Ladies and gentlemen, HCl is also known as a
Strong.
acid, which means what's it actually doing when it's in water?
Completely dissociating.
Into what principally?
H plus is the only.
So the concentration of H plus is 0.5.
Right, and if you know the concentration of H plus, or what's a synonym, what's synonymous with H plus? H3O plus, you know, when we assume it attacks water. And what can we do with H plus or H3O plus? We can take the negative log of it, and what will that give us? The pH. So I ask again, is A easy?
Yes.
Okay, what's B asking us for? The pH after 15 milliliters of NaOH were added. So what do we have to do there? Is that going to be enough to neutralize?
No.
Because they have the same concentration, right? But concentration isn't what determines it, right? It's the number of what of a compound? Moles. And if you have different volumes with the same concentrations, do you have the same number of moles? No. Now what about letter C? What can you guys tell me? What's going on with C?
C, the pH should be 7.
And why is that? Because the moles of each should be
Most of it should be the same because they have the same volume.
and the same concentration, right? And same volume, same concentration means the same number of, and so when you subtract them from each other, you get a big fat zero. Okay. And then what about D is interesting. Someone tell me what's happening with D. And keep in mind, we haven't done any math yet. We're just using our eyeballs and our brains right now. What does D tell us, guys?
It's the same thing, just with 45.
So that would mean that it would start to become basic
Why?
because you're adding more NaOH, more moles of NaOH than you have moles of HCl. So
And we know it's more moles because when we multiply, after we convert this to liters, when we multiply this times this concentration, its number is going to be higher than when we multiply any of these three, right? Okay, very good, very good. So this one should be, and is it going to be very basic or a little basic? What do you guys think?
slightly basic, not slightly, but
Well, look at what it is.
Very basic.
So remember, even tiny amounts, that's one of the reasons why, what did we learn about last lesson?
buffers.
Buffers. And remember, buffers are necessary because if a strong thing is unopposed, whoosh, right? Even if there's just a little bit of it. Yes?
So
So it would be very basic.
for C and D, they're just gonna like cancel out, right?
Yes, but not because, just because of the 30s. It's also
And we
because
have the same
of,
polarity.
right, yes.
Okay, that makes sense.
And I want to point out, in this problem, everything's samesies, right? So you just need to have the same of both to be neutral. But remember, the way numbers work, is it possible to have different concentrations and still neutralize each other? Yes, you would just need to have different,
Polarities. Or
well, that's what I said, they have
quantities,
different
like
volumes.
quantities.
Yeah, different volumes,
Volumes.
very good. And then that can adjust for each other, right?
Yeah.
So if one of them has a higher concentration than the other one, we're gonna probably have to use what volume of it? Less, right? Because to compensate for the other one having a lower molarity, we would use more of the other one, right? Okay, so let's do the math here. Guys, strong acid, 100% dissociation, right?
Yeah.
Yeah.
Okay, so we already discussed this. Letter A should be pretty straightforward, right? Because this is before we do any sort of titrating. Hey, what's up?
Hey, I got you got my email.
Yes, yes.
I'm able to interview when you
How long?
probably 5 minutes.
Ryan, do you want to go for 5 minutes?
Bye-bye.
It is 15 seconds to 9:55. You better be back in here by 10. All right. So now, find the pH after 15 milliliters of titrant were added. Oh, quick thing. You might want to write this down, guys. Titrant is whatever's up in the burette. So whatever you're adding, and let me show you guys actually what a burette is while you're writing. Whatever you're adding, guys, whatever your known is, remember we always add the known. Whatever your known is called the what, guys?
Titrant?
Titrant. So this is what we call a burette. What we're going to be using next class. Now, next class when we do this, don't you dare put this upside down. The numbers, when it's set up, should be right side up, okay? So numbers are right side up. No, it is not a mistake that the biggest number is at the
Bottom.
because a burette is all about how much you have added or lost from the burette. So it makes sense that it will increase as you go down, okay? Because it's how much you've lost from the burette that the burette measures. Okay, and so the way we use a burette, you take your, I'm going to just tell you guys now about all of this. This is called the stopcock, and you put it in the burette, okay? You know, for a couple seconds
Everyone held
there,
it in.
for a couple seconds there, this was my favorite class of all time. Because
Somebody ruined
for the briefest of moments, this was like the chosen one. This was the class where I told you what this part of a burette is called, and no one, not even a smirk. I was looking at your faces, not even a smirk.
Well, we have
It
masks
was
on
great.
too.
It
And then
was
you
so
stop for the
fucking
dramatic
beautiful.
pause and we
When
all
I
start
did
thinking
this
about it.
online last year, they turned on their microphones to laugh.
What's the name of Mr. Mike?
I was smiling because
After
you were
not
looking at it,
participating
checking if
all
you were
year,
laughing
just
or not.
black screens of
It
death.
was funny how no one reacted. I was like waiting for someone to laugh. and
No,
I
it
was
was
like,
great. I was so happy
like-
no one was reacting. But anyway, okay.
Wait, I thought the whole thing was
Favorite
about
class,
reactions.
Title stricken. Alright, so
"Oh,
anyway,
Marco."
anyway,
You gave us the opportunity.
Anyway, you
Where'd
take-
it go?
you take this part of
Peru.
your red,
What's it called again?
you take this part of your red, and you don't, Caroline, this part's always great, horrible, you don't jam it in and squeeze it in. You have to gently escort it into the tube.
You're making this worse.
Gently insert the stop cock into the hole.
Does anyone have any sympathy for what I have to go through?
Yeah.
Sometimes, like especially with the glass ones, That's why I always use plastic. Some of the glass ones, I don't even understand that one. But with the glass one, sometimes you have to add a little bit of lubricant to it. What is wrong with you kids? Okay. Anyway, with these burettes, you kind of have to, you have to gently make sure none of the rubber bands get messed up here.
Yeah, make sure the
Okay, that
rubber.
one was funny.
I don't get it. Okay, so you gotta make sure your biggest number is on the bottom, because when you read it, it should be right side up, okay? And you've gotta make sure the stopcock is closed, okay?
Wow, it's kind of smaller than I thought it would be.
Just remember, it's not, oh gosh, I can't either.
Why is it not called a stopper?
Why is it, yeah, why is it?
Not
why they
very
have to
hard.
add
Anyway,
The cock to the end.
you, the way you make this whole lab experience, the whole titration thing go, is you manipulate the stopcock to get, you open it up to add more, and then you close it up to stop the flow from it, and that is how we use it. And what goes up in here, we load it up with titrant. Which is what,
What's the stopcock made
What is
of?
a three-way stopcock?
No, I mean I'm actually being serious. What's it made of?
Three-way stopcock.
Looks like it's
How
made
about
of
we
glass.
stop?
No, but there's this white thing in the center. What is that?
Oh, white.
Yeah, like it'd be stopping it. What is it?
Plastic that
It's
gives
like
you-
our favorite, just so you know.
my fingers are itchy, I need to wash them. That's another thing, guys, remember, if your fingers feel itchy or if they're slippery during the lab, you're gonna come over and,
Very calmly start screaming and washing your hands.
no screaming, you're just gonna calmly come over and wash them, okay?
Yeah, but the screaming's funny.
If you're gonna wash your hands in that scenario, do you use soap or do you just rinse it?
You can use soap later in the process, but the first thing is to get as much water flowing as possible over it, because water, did you guys see where I put down my clicker? I feel like I put it down.
It's right there, it's right next to the Exxon marker.
Welcome back, sir. Hey, and you met your deadline, thank you. Alright, so anyway, here are our calculations. So, Ryan, don't worry, I did a little quick lab demo, so you didn't miss any of the lesson.
You didn't miss much,
I
right?
heard a lot of shouting.
You had a lot of what?
I heard a lot of shouting.
Oh, you missed it.
You missed it.
I know, you missed it.
Alright, so anyway, guys, here is our calculations for part B. Remember, part B is where we did not add enough.
Right.
So what's gonna still be left over afterward?
Somebody just go.
You're gonna have some HCl, because look, which number's bigger? Notice this has 2 zeros after the decimal.
I can read.
Alright, so, does anyone still need this slide?
Yes.
Okay, no problem.
Wait, so why is NaOH the titrant instead of HCl?
Oh, you could use either one, however, for this particular lab setup, the NaOH was being used as the titrant.
Okay.
And it does affect, it affects all the results and everything, but yes, you could do anything you want, any of the strong ones you want up in the burette.
Okay.
It's just, you gotta know which is which, because your known goes up in the burette.
Yeah, alright.
Wait a second. Is it actually true that like the indicator, like it comes from red cabbage?
One of the indicators, yes.
Why are you washing your hands so much?
So what I'm getting is.
I was handling a lot for the honors lab this morning, so I think I have a
They got a
lot
lot
of
than we
residual
did.
stuff on my hands.
Okay.
I agree with that.
What was the lab?
Yeah, what was their lab?
The reactions lab,
We didn't even get a reaction lab.
like double replacements.
No, we didn't get that.
What's up?
Okay, so if the indicator is like a weak base or weak acid, how is that supposed to be taken into account?
I haven't explained what the indicator is yet. But to answer your pretty amazing question, There's a reason why we did acid base 4 before this.
Oh, no.
Because
No.
indicators are in fact
Buffers.
buffers.
No.
Alright, so anyway, in order to finish off this one, it's not a true ice chart. It's just, all it is saying, we're just subtracting the two, like we already discussed out loud. We're just subtracting the two to find out that we have this much H plus. Because remember, we didn't add enough NaOH in this one. So guys, you take this, and before we do anything else, what do we have to do? We have to find the new...
Oh,
Because
that's
we
why my
actually
numbers were
added
off.
a significant quantity of NaOH, and NaOH is itself dissolved in water. And so
There
water's
it is.
volume is always additive. Okay, and so
Not
now
helpful.
we've got our new, see, it is a significant change because we went from 0.03 liters to now 0.045. That's a 50% increase in volume, so it is a really important thing. You gotta do your new volume. And then we're going to divide those two. Why do we divide them? Because that's the definition of molarity or concentration, right? It's what over what? Moles over liters. All right. Did we find the pH yet?
No.
Oh, there's even more work. What do we have to do now, guys? Take the
Negative
molarity
log.
and do what to it?
Negative log of it.
Very good, very good. We're going to take the negative log of the molarity, and that will give us our pH.
Actually, that's not bad.
Yeah, can you believe this is still only part B?
I kept redoing the calculation thinking that I was wrong when I had that exact number.
Good job, sir. So you remembered to take into account the new volume?
Yeah,
Good job.
but no. The issue is that when you add 15 more, it has to jump up to 7 now, which is a massive leap that I was like, whoa, I thought it would be at least breaking 1.
All right, so let's do part C. So part C requires no math, and it's because normally you would have to do math. I want to put that out there. Normally we would have to do math because your eyeballs aren't necessarily going to tell you when 2 moles are
Equal.
But can your eyeballs tell you here? Same
Yeah.
concentrations and same... Oh, actually that's not, but we knew from earlier, yeah, 30 and 30. So guys, both the concentration and the volumes are the same. Hey, welcome back. What? Okay, well, enjoy. Acid base 5, titration. Fairly straightforward.
No,
Right,
it isn't.
guys? Fairly straightforward.
It's horrible.
For sure.
No, it's actually not that bad.
Nah,
Yes.
it's doable, but still.
I found really nice videos I'm watching.
What was that?
Another fake currency pass.
It's not bad.
It's really not
Alright.
swollen at all.
Yeah.
I'm with white on this one. It's not that bad.
You can feel the difference. All right,
Between this and
so
buffers,
guys, normally we would do math here, but we don't have to because you can eyeball it. But normally you would, and what would you be looking for to get the same result, guys? We'd be looking for, what would we want, oops. Instead of this here, what would we have here if we did the math? For,
0.
It would be 0 for both of these, right? Okay. Okay, yeah, so pH 7, normally we would do the calculation, and then when you came out with 0, you would just know, oh, it's going to be pH 7 because that's 0 H3O plus would be water. Okay. Oh, and guys, this last bullet's interesting here. Why don't the spectator ions affect pH? It's because we had HCl, which is a very strong acid, and we had NaOH, which is a very, and remember, this very strong acids and very strong bases, their conjugates do not do what to pH?
They don't do anything.
They don't affect it.
They're
That's
so
why it's
completely weak that they don't care.
Yep, so that's why it's pH 7. Okay,
Also,
yeah.
wouldn't like the classic of the classic table salt, wouldn't that form because it's sodium and chlorine floating around? So if anything, they would just bounce each other and form just a very stable
If you dried
compound.
the water out, yes.
Yeah, but still, okay.
Alright guys, now this one we're going to add 45 milliliters, and as we've already discussed, this one's going to go past the what point? Equivalence point, right? Way past it. So we're going to find the moles of both. Notice the HCl has always been the same because it's the sample that's down in the flask. The NaOH though, we're adding more and more of it, so its amount, its liters change, its moles keep changing. What do you notice about these two moles, guys? The NaOH is larger. Right, so we can learn. You guys got it.
Why'd
Yes.
you run out up
Yeah.
to 23? It's 20. No, well, that whatever, doesn't matter that much.
Well, whenever you're doing calculations in a college level class or whatever, you're right, you would want to maintain the result in your calculator if possible, and then use that and not round till the end.
Yeah.
Alright, so let's move on here. So guys, notice, which one do we have left over? And because it's the OH, it's going to be a little tricky. That means we are going to need to find the what?
POH.
The POH, right?
Which is
Because we
the
can't
exact-
find pH directly. But then after we have POH, what do we do to find the pH?
Subtract it from 14.
Very good, we subtract from 14. So first we got to add the volumes up. Now it's up to 0.075 liters. Then we're going to divide these moles by these liters, which will give us 0.1 molarity. And then we'll take the negative log of 0.1. Is that our final answer, 1.0?
No.
No, because that's the POH. And what do we have to do? Subtract it from?
14.
So 14 minus the POH equals pH. Yes, what was that?
Like you.
Avi, question? Stretching. All right.
So the ice chart, like that could just that's just because like how I know it is just like you do whatever's great over.
Yeah, ice chart in these problems completely unnecessary.
Yeah.
But it's showing it just to give you kind of a familiar way
Yeah.
to know to kind of organize your thoughts, like with the H's
Yeah,
and all
'cause,
that.
like in the homework like answer keys, it just showed it as like just combined.
Exactly, yeah.
uh,
So, you choose your favorite method of doing it. There's no
Yeah.
right or wrong answer. Even all the times we used ice charts, they're not explicitly necessary.
Yeah.
They just make your thoughts really shown on paper, and it also signals to any teachers who are grading your work. Because a lot of them, that's the only way they know how to do it. So it signals to them that you know what you're
So
doing.
there's
Yeah,
another way of
alright.
doing it?
It's chemistry. There's always many ways of doing things. It's just, this is like, it's like a standard. Ice charts are like a standard, that are like a soft standard that people like to do. Okay, here we go, guys. These are important. You need to memorize what titration curves look like. So guys, a strong acid, strong base titration is going to have a really sharp increase and then level off. Someone tell me why. It's because what are we using for this titration? What and what?
Log. Oh, no, it's strong acids and bases, but the log makes the curve, right?
Isn't there a way of flipping that curve around?
It's the
Yeah,
nature
it's
of
because of how,
yeah.
because it's getting, your one is becoming really, really small, and then when you cross over that zero line, the other one is still really, really small.
yeah,
But then it like,
yeah, but it's the nature of how pH is calculated.
correct. So, as you guys can see, does it make sense if we're starting out below in the flask? Does it make sense if we have the acid down below? Does it make sense that our pH is all the way down here? And then, like he was saying there, guys, what explains this sudden rise? Because the amount of acid is getting really, really what here? And logs behave kind of really strangely at those low amounts. Welcome. Oh, guys, the dead middle of your somewhat vertical rise is also known as our
Equivalence point.
equivalence point. Excuse me. All right, and yeah, any questions about titration curve? Yes, sir.
No, there's a question to the lab that we're gonna be doing. Are we gonna be doing the setup today, or are we just gonna be doing setup and lab?
Let's see if we can finish today,
Okay.
because if I do, then yeah, we might as well start playing around back there.
Ooh.
Yeah, we could start playing around back there. And by playing, I mean working hard and labbing properly.
Of course, not playing around with hydrochloric acid and
Bianca?
stuff like that.
Well, what if you put an acid in a base?
And remember what we said, you can do either one.
Okay, but does it change?
Oh, I see why you asked it that way. Yes, great question. Basically, it would, and where would we start? We'd start up here, and then, woo, and then like
But
that.
you still have the same equipment.
Your equivalence point would be the same if they're both strong, because the equivalence point for two strongs is 7.
Oh, wait. I missed.
And guys, if you change out one of those for a weak one, it'll shift it, either up or down. All right. Now, guys, one more thing to notice before we move on. What do you notice about this region? It's really, really relatively, even if it does have a curve, it's very flat, right? And then what about up here? Is there much of a curve?
No.
Like there could be, but to our eye, it looks relatively straight, right? It'll look different for a weak acid, weak base. Okay, here's some more notes added in. This is less than 1.5 over this region because most of the base required to reach the equivalent point is added here. And then this part has a very, very, like for a very tiny volume, look, it's like a very tiny volume, you have a really sudden change in pH. So guys, this vertical section and this note here explains why titration isn't just science, it's also a very, very difficult skill to master. Because you have to very carefully add the volume. Because, guys, do you notice, is there a huge volume change between like here and here? And look what happens. Even an extra half of a drop does what? So you have to be very, very careful trying to get to this point. Yes?
So on the test, would we have to match graphs to their base titration, like their titrations?
So I'll give you an example of what they could say. They could give you a graph and say, which of the following is this? Like, okay, let me give you a setup. Cindy, scientist, has conducted a titration, but she was a klutz and mixed up the chemical bottles. Here's the graph that her equipment gave her, because she used a digital thing to do it, on a computer and all that. Which of the following explains which bottles were used? And so, if the graph looked like this, you would know that she put the strong acid
With the strong base.
on the bottom, but yes, with the strong base, and that the strong base was in the burette.
Oh, okay, I didn't know it mattered top and bottom.
Well, top is what you're adding,
Oh.
because the
Okay.
burette goes above.
So what if you have a strong base and then you add a strong acid? Does the chart change?
So that's what Bianca was saying. It would be flipped.
Oh.
Like this region would be up here, and this region would be down here.
Oh, okay.
Like you can almost think of this, like you know how in physics, guys, what do we use at the bottom a lot of the time?
No, I don't take.
We do time a lot on the bottom, right? We do time. You can almost think of, in these things, you can almost think of volume as time, right? As you're increasing the volume, the change is happening, right?
Mr. White.
Yes.
So, what was I going never mind.
It's okay, when you think of it later, just interrupt me, okay? Alright, so let's do an example here. 31.25 milliliters of 0.250 molarity HCl was titrated with an unknown concentration of NaOH. The end point was reached when 32.75 milliliters of NaOH was added, final concentration of the titrant. Okay guys, this is one of those bizarre ones where the known was actually in the bottom and the titrant in the burette was the unknown. This isn't typically how we do it, but you can still do the math because we knew exactly what was down in the flask, according to the problem. So what this problem is kind of trying to show you is a lot of this math is universal. Okay, you can play with things a little bit. So we have to figure out what the moles of the HCl in the solution initially were. We'll take this 31.25 milliliters, and what are we turning it into first before we do anything else? Liters. And then we take this molarity of HCl and break it up into moles and liters by putting the number moles over 1 liter. That'll give us the moles of HCl. And then we're going to find the concentration of the NaOH titrant. And the way we do that is, guys, it says we had a titration done here. And it says the what was reached. Which means the color changed. So guys, the color changing means that this HCl is in fact the exact same as the, and so look, what number did we use right here? We used that number. But instead of labeling this as HCl, what did we label it as? And boom, that's what we get. Yes, sir.
So if we have a test review day, would it be possible to look at like our previous test again, or are those like packed away, like filed away somewhere and like?
I could potentially dig them out of the deep Indiana Jones style file.
Because like my biggest problem with like the test is like remembering how the questions are, like how they ask some of the questions.
Mm-hmm.
So I feel like being able to look at those would be helpful.
Yeah, if you want.
And looking at that weird smudge question.
Your favorite?
Like,
God,
weird-
that
Everyone's
one's.
favorite?
It's a 3 point, but I got it wrong on like
I
3
got
of
it
the
wrong 4
tests.
times in a row.
Why do you think I keep using it?
And you changed it last
It's
time.
the question is always about a smudge in the glass or
Well,
something.
Like he rewords
It's
it.
always
He's
a-
like his thesaurus, and
like-
he rewords the
Like
question.
like a fingerprint or something.
sir.
Yeah.
It's horrible.
How come the moles are the same?
Oh, it's because it's at the end point. Like the whole idea, the whole underpinning of titration, like the word titration and like the whole reason we do it, all that, it comes down to one simple truth, is that when that color changes, we assume that acid equals base moles.
Wouldn't that be the equivalence point though?
Yes, but that's why I kind of began with the lesson with. We use endpoint and equivalence point the same.
Oh, okay. I'm not.
Like they're not the same, and we understand that.
Okay.
But in practice, we use them as though they're the same because it's the only way to do it.
Okay. Alright.
Like machines can do it correctly, but then machines are often miscalibrated. So it ends up that this is still the best way to do it. All right, guys.
No, I'm so right.
No problem. Guys, so this way is kind of cumbersome, right? Where you find the moles and then you divide those moles by the volume and all that. How would you guys like it if I showed you a much easier and simpler way to do this every time, get it right every time the word titration is uttered?
I would
Please.
Okay.
No. Wait, that'll be an art. Oh.
Mm.
It's like minivan.
Shit that I was doing is
All right, so
Minivan.
as you guys can see,
No.
no, listen, this is easy. Look, it's like a simple formula. Instead of 2 lines of stoic style calculations, instead you should do boom and done. And you don't have to convert to liters for this either. Do I need to say any more? So for this problem, guys, how many milliliters of HCl do we have?
31.25.
Oh,
And then what's the molarity of HCl?
0.25.
Now guys, the N only matters. The N only matters if you're using a polyprotic. That's another reason this is just
What is that?
like where it has more than one H, like H2SO4.
Oh, yeah.
What is
Sulfuric
it called?
acid.
A polypropic?
Polypropic.
It's been mentioned in the notes several times now.
Come on, Victoria, get with the game.
Yes, it has, Victoria.
When?
It was like 5.55.
And it's like numerous questions on the homework.
Oh, is that the one where there's multiple where there's multiple like reactions that happen?
Oh, it's that
I
way.
did do my homework. Well, I did not see that.
Polypropic.
Anyway, the N here is only if you're using a polyprotic, but the vast majority of the time we are using,
Monoprotic.
so you don't even need to worry about the N most of the time. But if you do, you just put the 2 there. Okay? Equals.
Oh my god, it works. I mean, like, it's Mr. White, so.
Okay, so guys, calculator time, 0.250 times 31.25. What?
Wait, 7.8.
7.8?
Yes, 125.
I got like 0.001 off, but yeah.
Wait, what are we supposed to do right now?
Okay, what do I divide both sides by?
32.75.
And what is now M2?
0.239. Don't you get that?
Is this just like hacking the entire system?
That's the same thing that's there.
Yes.
Yeah.
No, that's my point, is this is much easier. If you just remember, guys, when you see the word, when you see the T word, titration, what are you going to use?
Minivan.
Minivan.
This is not on the reference sheet, so please write this down.
Is this your creation?
No.
Did you think Mr. White was making innovations in the world of titration?
No, this is just how chemists always get through it. And then they always teach youngins this awful way.
So they use the easy way, but they teach everyone the hard way.
Wait,
Right, and you're not a chemist until you kind of quietly make a friend who teaches you.
So are we now chemists?
Your friend?
Wait, I gotta.
Hey, what's up, sir?
So N is the number of H's.
Yeah, N is the number of H's, and you know what you can do? You can practice that like on the homework. If you see a question of polyprotic, you can kind of practice it and try to get the answer they get by doing this and figure out, kind of mess with it a little bit. But yes, the N helps you. Most of the time you don't need the N, but if it's a polyprotic, you're going to be so thankful you knew this formula because this will save your life. Polyprotics are they're so hard to do it in your head without this. Yes, sir.
But it's also worth recognizing that polyprotics only apply to H's that are leaving, because like Chaku technically has 4 H's, but only one of them is going to reasonably be broken off.
That's what it. The H's that are in play.
Yeah, just
Yeah.
no.
Good point.
Oh, I think I must have missed it. The N.
The N is only necessary if it's a polyprotic.
Okay. Oh, and then you put the amount of hydrogens
Yeah,
that there are.
and when you're doing the homework and practicing and stuff, you can play around with the polyprotic with this equation. Some people actually with polyprotic prefer to do it the long way, just to kind of keep everything. I think it's dumb. I just do it like this. Okay, but yeah, that's something you guys can play around with. Guys, highly recommended. What do we do for titration?
Minivan.
Don't do it.
And guys, is M1 V1N, M2 V2N on the reference sheet?
no.
They are not.
So you definitely want to study that.
What is a half of the ones you put?
Don't ask these questions.
We're getting there. Alright, so let's do another example. The titrant from the previous example was used to titrate a 28.65 milliliter HBr solution. The endpoint was reached after 34.85 milliliters of titrant were delivered. Find HBr in the solution. You guys want me to do my way with this one?
Yes.
Yeah.
Okay, so can someone remind me of this, because I have to use this molarity for this question. You guys have this written down?
Yeah.
Okay, I'm gonna erase this. Okay, in the question, how much titrant does it say is added here in this?
34.85 milliliters.
Okay, and then what was the concentration we calculated last?
0.39.
239? Okay, and then it's 28.65 milliliters HBr, right? Okay, let's do this, guys. 0.239 times 34.85.
You said 0.239?
Yeah, 0.239 times 34.85.
0.29. 0.291.
Is
You
that
wanna go to
right?
the third.
No,
I could be wrong.
Wait, are you talking about the final answer?
Final answer.
No,
Final
I'm just
answer.
trying to do these.
Oh no. The other one was 8.329.
Is that what you got, sir?
I got that as well.
Okay.
I swear to God, if it's another
Well,
fire
there-
drill.
Bobcats, apologies for this interruption. Bernard School's fire inspection is on campus working with our system. Please know that should any fire alarm go off, we will make an announcement that it is just the inspectors working on the alarm system. So at this time, please do not evacuate until the announcement is made on whether it's a byproduct of the inspection or a real real alarm. Thank you very much. We'll come back on and let you know when the inspectors have left campus. Thank
Okay,
you.
we got the
Bye-bye.
idea. Okay. All right, guys, divide, please. What did you get, Michael?
0.291 to round up.
I got the same.
Okay, so this very slight difference is probably because they used the wrong rounding and this stuff. It happens. But as you can see, the numbers are basically identical.
I ended up getting like closer to that.
You got
because,
this one?
Yeah, I did.
Okay, so it could be sometimes the calculators.
Yeah, because
mess it
I
up.
did
Like maybe I rounded something different. I don't know. It's so close. It
I'm
doesn't
just
matter
gonna
that
call
much.
it 290 just in case. That
Cool.
way it's kind of.
Yeah, because I did 34.85 times 0.23, and that's divided by 28.65.
How do you know that the second volume is 28.65?
Oh,
It tells you.
So that's a great question. Basically, it didn't have to be the second volume. I could have done that one first, but I would have had to make sure that the M was with it. Like the
Yeah.
mysterious one we're searching for, the N. If it was on this side, it would be M1, but it would still be a variable M1, and then these two would be over here.
Okay, so
So it's not important whether it's M1 or M2. What's important is that the pairs are with what they're supposed to be with.
yeah, I don't understand why 28.65 is with M2
Because they want you to find HBr. See, 28.65 HBr.
okay.
So that is a great point, Victoria, and they will mix them up on you. So you have to read it carefully and match M1 with the correct V1 and M2 with the correct V2.
Okay, that makes sense. Thank you.
Anything
So,
else?
yeah, guys, again though, if you like this way better, this is the official way. This is the scientific way. This is the moles way. Like this way is the way you do it to understand that moles equal moles,
Would
right?
we get points off for not doing it this way on
No,
the
no,
AP
no, no.
test?
This way is almost like just short of being the standard way of doing it.
Okay.
It's just that this way has the added bang for your buck where it's showing you the science behind what's going on. That's why this way is important.
Cool.
But this way is actually useful. So you kind of see the difference there?
Yeah.
They give you the same answer. I teach you both ways And which way am I expecting most of you to do?
Minivan.
Minivan.
Am I gonna mark you wrong if you do the science-y way?
No.
Absolutely not, I can't mark you wrong for this. However, you're more likely to get this one wrong than this one. All right.
I love minivan.
Another example here, guys. A 3.145 gram sample of KHCH4O4 was dissolved
What
in
even is
water
that?
and used to standardize an NaOH solution. The endpoint was reached after 42.55 milliliters of titrant was delivered. Okay, so first things first, whenever you see grams in this class,
It's gotta turn into moles.
you always gotta convert it into moles. Very good, Michael. So that's our first step, is to convert that one into moles.
Wait, hold up. Why is the grams very similar to pi?
No relation.
3.14.
Like it's
No
just kind of off, just a little.
No relation.
This
All
isn't
right,
the
so
first time
then,
you've
guys, once
noticed
we know how many moles of KHCAH4O4, we are also going to need to find the concentration of the NaOH. And notice it says this much titrant was delivered. So we take this number, we've done this before, and we scratch out the KHCAH4O4. What do we put there instead? And the reason we can do this is because it very specifically says in the problem that we reached the endpoint. And when you reach an endpoint or equivalence point, whatever you want to call it, in this class we treat them the same, even though they're not the same. Whenever you reach that point, we say that the moles of acid equals the moles of base.
Mr. White?
Yes.
So minivan only works with strong base, strong acid, right?
No, it works with everything.
But what about this? Since
What's the titrant here?
Well, in this case, because they gave you grams, and see, we don't have,
we
we
would
don't have
only be able to
concentration
use
ever of
moles,
this, so
yeah.
it's better. In fact, you see, here's the trick with this one. They never actually gave us the volume of this one. So,
That makes
to your point, this is one of those rare cases, and another good reason to actually learn both ways. This is one of those rare cases where you can't do minivan.
Yeah, okay.
Okay. Any questions about this one, guys? This one is a little tricky because it kind of leverages the fact that you have to remember to convert grams into, and then you have to remember that at the end point, moles of acid equals moles of base, and then you can take the moles of acid, scribble it out and put the base in there, and then divide it by the volume of it added, and that gives you the molarity.
So you can't use minivan for this.
You cannot.
And I thought I could forget this entire thing, but
Yeah,
no.
me too. I was so happy.
No, but you still have minivan for most of these. All right, any questions now on this one, guys?
Still doing some work.
And, yeah.
You said they're fall.
I'm getting, like, I'm using minivan, I'm getting it, like, within, like, 0.01, but, like, I don't know. It's significant, or I don't know how significant it is.
You're talking about on this one?
Yeah, when I use
Well, what did
minivan.
you use for the volume? Because, see, they only gave us one volume here.
Oh, wait, sorry, we're still on one, aren't we?
Oh, you're on two?
Yeah, I was looking at two, yeah, but,
Okay, so we're going to use this titrant, this molarity right here, So remember this one, guys, 0.3619 is what we're using here. Is that what you used, sir?
Yeah.
And you paired it with the 28, right?
Yeah. And I also didn't use the shortened version there. I just used like the version of my calculator that like.
Okay, yeah, and you got 0.4?
Yeah, I got 0.4055.
Yeah. So
Okay,
as you
that's
guys
close
can
enough.
see, guys, as Charles has just demonstrated, can you use minivan with weak acid or weak base titration?
Yes.
Yes, you can.
But not with grams.
But not in specifically what example 1 presented us with. Yes, correct. Yeah, example 1 was like kind of a spoiler, right? But most of these you can, as long as you've got both volumes. And then you do have to have one of the molarities.
So like in the AP exam, by at one point does like a few numbers off become.
Well, when you get to the AP exam, it shouldn't really be off at all,
Okay.
because part of the problem here is a gentleman who did these calculations originally probably used a different periodic table than what we have here.
Okay.
And so that's why his numbers throughout the entire year are sometimes slightly off.
Okay.
But on the AP exam, what you'll find is, and in fact you probably guys have noticed this on our tests because I use AP questions, and we use the actual AP reference sheet, the numbers are like exact to what you see on the key if you got it right.
Yeah. Okay.
So because when all the numbers are standardized, we're all using the same stuff, your numbers should be almost identical.
Yeah. That makes sense.
Unless you're rounding while you do it. Then
Yeah.
that can introduce a little bit of error. But as long as it's not too bad, you usually be marked right.
All right. Cool.
But that's why I highly recommend never round until the very end,
Yeah.
if possible. And if it's not possible, write as many digits as you can for an interior number.
Yeah.
All right, guys. So yes, you can use minivan for this one. All right. Yet another example. A 3 times 10, why don't they just say 30 milliliter sample of 0.5 HC2H3O2 is titrated with 0.5 molarity NaOH. Determine the volume of 0.5 molarity NaOH that must be delivered to reach the, Bianca's favorite word, the half equivalence point.
That's
Wait,
3
there's
words, not
equilibrium
1.
in this. I don't like that.
And the pH at half equivalence point is measured to be 4.74. Find the pKa for HC2H3O2. Identify the main species that are present in the solution being titrated at the half equivalence point. Guys, are you ready for a spoiler?
No.
If you have NaOH up in the burette and you're using the stopcock to add more of it into your acetic acid, then the half equivalence point is when you have added enough NaOH to it to kill off half of that acetic acid. Guys, if we react forcibly half of the acetic acid to its conjugate, what have we now created?
Salt.
The salt of it on the other side, which meets the definition of a
Buffer.
buffer. And why is the half equivalence point so key? What does that unlock for us?
Because that means that you have equal amounts of salt and buffer in the solution.
Which means then our pKa and our pH will be
Equal.
but only at the half equivalence point. And it also opens us up to using what equation?
H&H.
Henderson-Hasselbalch. Very good, very good.
Hold up. Also, wouldn't, like, by definition, if they're at the same molarities, wouldn't you only need half the milliliters of the NaOH in order to get to that halfway point?
Correct.
Cool.
But of course, most of the time they're not going to be the same.
Got it.
It's just in this case, yeah. And so let's so moles of the solution initially, and then the volume of NaOH that must be added. Guys, why did it say 0.015 here? I thought we were supposed to use that exact same number right here.
Nah. Looking for
Because
the
we're not
half.
trying to reach equivalence, we're reaching,
Half equivalence.
and because it's half equivalence, what do I need to turn this into? 0.0075. We have to divide this number by 2.
Why?
Because we want the half equivalence point.
Come on, Victoria. Get with the game.
That's because we want the half equivalence point.
It just it didn't register.
All right. So now to Michael's point earlier, notice 15 milliliters is half that volume, and that worked out because their molarities were the same. But Michael, as I was telling you, I'm showing you the math here because most of the time you have to do the math to figure that out. All right. So that was the answer to part A. I'll give you guys a second because some people are still writing. Okay, we're getting there.
Mr. Moore,
Yes, sir.
this is kind of a stupid question, but like with dimensional analysis, like on the bottom there, why is it that with the moles and liters you can just like switch it around?
Oh, that's the beauty of it. Molarity is moles over liters, right?
Yeah.
So whenever you're presented with a molarity value, you always can treat it as whatever that number was over 1 liter.
Yeah.
And that is beautiful because then you can just flip them around anytime you need to use it as a conversion.
Okay. Alright.
So that's why it's important to kind of realize that the way math works. When you have two things divided to equal another thing, you can say that other thing is the same thing as that number over 1 of whatever is divided.
Yeah. Okay.
All right, so part B, it wants to know the half equivalence point, find the pKa. Guys, did we even have to show Henderson-Hasselbalch here?
Oh.
Probably a good idea though, because that's a lot faster than saying that when you have a buffer, pH equals PA, right? That takes too long. What's a much faster way of justifying your answer? Writing real quick out the,
And H&H.
and then you just cross this out and do this. That's a lot faster, right, than trying to explain it? Yes?
I'm totally paying attention to you, but like the video that I'm watching says like the half equivalency point is, okay, like the number of moles of the conjugate base is equal to the number of, the number of moles of the conjugate acid are equal to the number formed equal the number of moles of the base, right?
Correct.
The
So,
conjugate acid equals the number.
yeah, and that's because we want these two to be the same, and then they cross out and log of
Could
1.
I just use that logic and just find one and not do this and that?
I mean, what you're saying would work
Like, could I just
sometimes, but you got to spend time studying it.
What you're saying is that it could work.
Well, yeah, that's
If I get lazy.
what you're talking about is what it is, but you're looking at it a different way than we're looking at it from the lens of titration.
But it still works.
Well, yeah, but you don't want to get all this stuff wrong. Okay, so guys, pKa equals pH when this equals this, and which is literally what you were just saying.
So.
Okay,
it does
so anyway,
work.
moving on. I don't have time.
So I can't use it. That's
Identify the
what I'm
main
getting
species that are present. Guys, at half equivalence, we already said that what is equal to each other? These two. So are these two going to be there?
Yeah.
Yeah, because they're both equal. And guys, why does it list Na plus here?
Because wasn't that part of the salt earlier?
Yeah. And then
Wow.
H3O plus is going to be in there because we have not reached the full
Equivalence.
equivalence point yet. So there's still going to be H3O plus in there.
Because it's still pretty acidic.
Because it's a weak acid, so even though it's weak, it still does a little bit, so it'll still be there. That's why it's below 7 on the graph.
Our acid buffers made from acetic acid is very, very common. This is like the 3rd or 4th buffer equation that we've done with
Acetic
acetic acid.
acid is just really easy to work with, and it's also vinegar.
So it's everywhere.
Right, so it's used a lot.
Okay.
Okay, real quick guys, weak acid, strong base titration. Guys, is this line right here as straight as the lines we saw earlier?
No.
And this can be explained because it is a
Weakling.
weak acid. And the midpoint of a weak acid being titrated, the midpoint of this horizontal-ish thing is known as the half equivalent. So if they give you a graph and tell you